Chapter 14, Solids, Liquids, and Gases. So the big idea for this chapter is that each state of matter, solid, liquid, or gas, has unique properties defined by the motion of its particles. Matter and thermal energy. So our main idea for this section, matter can exist as a solid, liquid, gas, or a plasma. The real world link here, water can be a cool, refreshing drink, a hard surface for sliding on, or a dangerously hot gas. How water behaves depends on its state of matter. Now, as I go through the rest of this, if you notice these numbers here, like our number 1 and our number 2, those refer to questions on the reading guide. So you can look at those numbers and the answer for that question should be somewhere near that number. Okay, so kinetic theory. You encounter solids, liquids, and gases every day. Look at figure 1. Figure 1's down here. It's a pitcher of sweet tea and some glasses with ice in them. Can you identify the states of matter present? The tea is in a liquid state. The ice cubes dropped into the tea to cool it are in a solid state. So the ice cubes are in a solid state, and surrounding the glass as part of the air is really water vapor in the gas state. How do these states compare? So the gas state. To understand the states of matter, we must think about the particles that make up matter. Consider the air around you. It is composed of nitrogen, oxygen, and water, along with other gases. These atoms and molecules, the particles that make up the air, are in constant motion. The kinetic theory is an explanation of how the particles in gases behave. So that's what kinetic theory is. To explain the behavior of particles, it is necessary to make some basic assumptions. The assumptions of the kinetic theory are as follows. So, number 1, all matter is composed of tiny particles, atoms, molecules, and ions. Number 2, these particles are in constant random motion. Number 3, the particles collide with each other and with the walls of any container in which they are held. And number 4, the amount of energy that the particles lose from these collisions is negligible. So we don't really worry too much about the energy lost. Now, figure 2 demonstrates the kinetic theory showing the particles that make up a substance in the gas state. So we have the gas state right here. And we have these particles that are all sort of going in random directions, like these are going this way, these are going this way, this is going this way, etc. So these gas particles are just moving everywhere. So because the particles are in constant motion, colliding with each other and with the walls of the container, gases do not have a fixed volume or shape. So they do not have a fixed volume or shape. Okay? Instead, the particles that make up a gas spread out so they fill the container that they are in. So the liquid state. Although the kinetic theory explains the behaviors of gas particles, some of the assumptions of the theory apply to liquids and solids as well. The particles of a substance in the liquid state, shown in figure 2, so liquid state will be right here, are also constantly moving. So again, the particles of a substance in the liquid state, shown in figure 2, are also constantly moving, although they are not moving as quickly as they would be if the substance were in the gas state. Therefore, the particles that make up a substance have less kinetic energy when it is in the liquid state than when it's in the gas state. So liquids have less kinetic energy than gases. Because they have less energy, the particles are less able to overcome their attractions to each other. They can slide past each other, allowing a liquid to flow and take the shape of its container. So liquids do take the shape of their container. However, because the particles that make up a liquid have not completely overcome the attractive forces between them, the particles cling together, giving the liquid a definite volume. So liquids have a definite volume, but they take the shape of the container. Okay. So the solid state. Unlike a gas or a liquid, a solid has a definite shape and volume. So solids have a definite shape and volume. The particles that make up a solid are closely packed together, as shown in Figure 2. So our solid in Figure 2 is right here. They're still in motion, but they have so little kinetic energy that the particles are unable to overcome the attractions to each other. So these have very little kinetic energy. So the particles in a solid have very little kinetic energy. Many solids are crystalline, which means their particles have specific geometric arrangements. So crystalline means that the particles have specific geometric arrangements. Figure 3 shows the geometric arrangement of ice. Notice that the hydrogen and oxygen atoms alternate in the arrangement. So that would be our arrangement right here. So thermal energy. Think about the ice in Figure 3. So if we look back at Figure 3, again, Figure 3 is right here. We have the ice, we have our crystalline ice here. So think about the ice in Figure 3. How can frozen solid ice have motion? So think about it for a second. It's solid. How does it have motion? The particles that make up solids are held tightly in place by the attractions between the particles. These attractions give solids a definite shape and volume. So there we see again, definite shape and volume for our solids. However, the particles that make up a solid are still in constant motion. The particles' thermal energy causes them to vibrate. So we have thermal energy, which causes these particles to vibrate. Thermal energy is the total energy of a material's particles. This includes both the kinetic energy of the particles as well as their potential energy. Energy from the motions of individual particles and energy from the forces that act within or between particles are both forms of thermal energy. Energy from the motion of an object as a whole and energy from its interactions with its surroundings are not thermal energy. Temperature. Temperature is the term used to explain how hot or cold an object is, and temperature represents the average kinetic energy of the particles that make up a substance. On average, molecules of water at 0 degrees Celsius have less kinetic energy than molecules of water at 100 degrees Celsius. So changes of state. What happens to a solid when thermal energy is added to it? Think about the iced water in Figure 4. The particles that make up the water are moving fast and colliding with the particles that make up the ice cubes. So those collisions transfer energy from the water to the ice. The particles at the surface of the ice cube vibrate faster, transferring energy to other particles in the ice cube. So the water molecules, we could think about the particles of water right here, hitting the ice cubes, hitting the particles of the ice cube, causing these to vibrate more, and then that energy is then transferred into the rest of the ice. So melting and freezing. Soon the particles that make up the ice have enough kinetic energy to overcome the attractive forces holding them in their crystalline structure. The ice melts. The melting point is, so the ice melts. The melting point is the temperature at which a solid becomes a liquid. So the temperature at which a solid becomes a liquid is the melting point. Energy is required for the particles to slip out of the ordered arrangement of a solid. So the heat of fusion is the energy required to change a substance from a solid to a liquid at its melting point. The transfer of energy between particles of liquid and particles of solid causes the ice to melt. But what happens to the particles of liquid after they collide with a solid? Well, they slow down because they have less kinetic energy. As more of these collisions occur, the average kinetic energy of the particles of the liquid decreases and the liquid cools. So that's how ice cools a drink. Freezing is the reverse of melting. So when a liquid's temperature is lowered, the average kinetic energy of the molecules decreases. When enough energy has been removed, the molecules become fixed in position. The freezing point is the temperature at which a liquid turns into a solid. Vaporization and condensation. So how does a liquid become a gas? Remember that particles that make up a liquid are constantly moving. When particles move fast enough to escape the attractive forces of other particles, they enter the gas state. This process is called vaporization. So when particles move fast enough to escape the attractive forces of other particles, they enter the gas state, and that is vaporization. Vaporization can occur in two ways. You have evaporation, you have boiling. The process in which a gas becomes a liquid is called condensation. Condensation is the reverse of vaporization. So evaporation occurs at the surface of a liquid and can happen at nearly any temperature. So evaporation occurs at any temperature. To evaporate, particles must be at the liquid surface and have enough kinetic energy to escape the attractive forces of the liquid. Boiling, which is shown in figure 5 over here, boiling is the second way that a liquid can vaporize. Unlike evaporation, boiling occurs throughout a liquid at a specific temperature. So boiling occurs at a specific temperature, depending on the pressure on the surface of the liquid. So boiling point's not always the same temperature. If you lower the pressure, you also lower the boiling point. If you increase the pressure, you increase the boiling point. So the boiling point of a liquid is the temperature at which the pressure of the vapor in the liquid is equal to the external pressure acting on the surface of the liquid. This external pressure pushes down on the liquid, keeping particles from escaping. Particles require energy to overcome this pressure. The heat of vaporization is the amount of energy required for the liquid at its boiling point to become a gas. Sublimation. At certain pressures, some substances can change directly from solids into gases without going through the liquid phase. So sublimation is the process of a solid changing directly to a gas without forming a liquid. So figure 6 shows frozen carbon dioxide, which is also known as dry ice, which is a common substance that undergoes sublimation. That's why it's called dry ice. It does not form a liquid first. Sorry, I had to pause there a second. I was looking at my note I made over here, and apparently I had a typo here. This is not sublimation. Deposition is a phase change in which a gas changes directly into a solid. So that's the opposite of sublimation. So sublimation, the opposite of that is deposition. If something goes straight from a gas to a solid, like water vapor freezing directly onto your windshield without going through a liquid phase when you have frost forming. Anyway, moving on. So heating curves. A graph of temperature versus time for heating of 1.0 kilograms of water is shown in figure 7. So this type of graph is called a heating curve. It shows how temperature changes over time as thermal energy is continuously added. So we have time going this way, we have temperature going this way. Notice the two areas of the graph where the temperature does not change. So area B here and area D here. The temperature does not change. At 0 degrees Celsius, which is right here, you have melting occurring. The ice melts. Okay, so ice melts at 0 degrees Celsius. All of the energy put into the ice at this temperature is used to overcome the attractive forces between the particles. The flat line on the graph indicates the temperature remains constant during melting. After the attractive forces are overcome, the particles move more freely and their temperature increases. At 100 degrees Celsius, water is boiling. So up here we have water boiling right here. Okay. The temperature remains constant again, and the graph is flat. All of the energy that is put into the water goes into overcoming the remaining attractive forces between the particles. When all the attractive forces between the particles are overcome, the energy goes into increasing the temperature again. So plasma state. So far you've learned about the three familiar states of matter: solids, liquids, and gases. However, there is a state of matter beyond the gas state. Plasma is matter that has enough energy to overcome not just the attractive forces between its particles, but also the attractive forces within its atoms and molecules. The atoms that make up a plasma collide with each other with such force that the electrons are completely stripped off the atoms. You may be surprised to learn that most of the ordinary matter in the universe is in the plasma state. Every star that you can see in the sky, including the sun, is composed of matter in the plasma state. Most of the matter between the stars and galaxies is also in the plasma state. The familiar states of matter, solids, liquids, and gases, are extremely rare in the universe. Thermal expansion. Have you ever wondered why a concrete sidewalk has seams? When thermal energy is transferred to a concrete sidewalk, the concrete expands. Without the seams, a concrete sidewalk would crack in hot weather. The kinetic energy, or the kinetic theory, can help to explain this behavior. Recall that particles move faster and farther apart as the temperature rises. This separation of particles results in an expansion of the entire object, known as thermal expansion. So thermal expansion is an increase in the size of a substance when the temperature is increased. Substances also contract when they cool. So if you heat something, it expands. If you cool it down, it contracts. So thermometers. A common example of liquids undergoing thermal expansion occurs in thermometers, like the one shown in Figure 8. The addition of energy causes the particles that make up the liquid in the thermometer to move faster. As their motion increases, the particles that make up the liquid in the narrow thermometer tube start to move faster apart, or further apart. So the liquid in the narrow tube in the thermometer starts to move further apart, and this causes the liquid in a thermometer to expand and rise as the temperature increases. So I kind of messed that up, but basically the whole idea is the liquid in the thermometer is heated, it expands. As it expands, there's nowhere for it to really go except up this very narrow tube, very narrow little capillary tube that the liquid can go up. Hot air balloons. An application of gases undergoing thermal expansion is shown in Figure 9. So we have hot air balloons down here. Hot air balloons are able to rise due to the thermal expansion of air. The air in the balloon is heated, causing the distance between the particles that make up the air to increase. As the hot air balloon expands, the number of particles per cubic centimeter decreases, and this expansion results in a decreased density for the hot air. Because the density of the air in the hot air balloon is lower than the density of the cooler air outside, the balloon will rise. So this is like the air outside. This is the air inside. Well, it's kind of hard to see that. The air inside. So the air inside is less dense than the air outside, so that will cause the balloon to rise. Water's strange behavior. So ordinarily, substances contract as their temperature decreases, or as their temperatures decrease. However, an exception to this rule is water. Over a small range of temperatures, water expands as the temperature decreases. At first, it behaves like other substances. As the temperature begins to drop, the particles that make up the water move closer together. And this continues until the water reaches about 4 degrees Celsius. Water molecules are unusual in that they have highly positive and highly negative areas. So water molecules have positive and negative ends. These charged regions affect the behavior of the water. As the temperature of the water continues to drop under 4 degrees Celsius, the molecules line up so that only positive and negative areas are near each other, as shown in Figure 10. So we have the water molecules lining up. And really, you have a water molecule like this. This is our oxygen. These are our hydrogens down here. The oxygen has a negative charge. The hydrogens have a positive charge. So the oxygens are red up here. The hydrogens are blue. So they start to line up with the hydrogen pointing towards, each hydrogen is pointing towards an oxygen atom. Anyway, As a result, empty spaces occur in the structure, so water expands as it cools from 4 degrees to 0 degrees Celsius and becomes less dense than liquid water. And this is why ice floats. So really this whole thing right here is why ice floats. Because water expands as it cools from about 4 degrees Celsius to 0 degrees Celsius and becomes less dense than liquid water. And again, that's why ice floats in liquid water. So solid or liquid. Other substances also show unusual behaviors when changing states. Amorphous solids and liquid crystals are two classes of materials that do not react as you would expect when they change states. So amorphous solids. So ice melts at 0 degrees Celsius and lead melts at 327 degrees Celsius, but not all solids have a specific temperature at which they melt. Consider a stick of butter. Instead of having a specific melting point, butter softens and melts over a range of temperatures. It does not have a specific melting point. Some liquids or some solids are like butter. Instead of having a specific melting point, they soften and gradually turn into a liquid over a range of temperatures. These solids lack a crystalline structure and are called amorphous solids. One common amorphous solid is glass. So glass is an amorphous solid. Liquid crystals. Liquid crystals form another group of materials that do not change states in the usual manner. Normally, the ordered geometric arrangement of solids is lost when the substance goes from the solid state to the liquid state. Liquid crystals start to flow during the melting phase, similar to a liquid, but they do not lose their ordered arrangement completely, as most substances do. Liquid crystals will retain their geometric order in specific directions. Liquid crystals are placed in classes depending upon the type of order they maintain when they liquefy. They are highly responsive to temperature changes and electric fields. Scientists use the unique properties of liquid crystals to make liquid crystal displays, or LCDs, for cell phones, calculators, and notebooks, computers, shown in Figure 12. LCD screens are composed of individual crystal picture elements, or pixels for short. Varying the amount of electricity that passes through the pixel determines how the crystals are aligned and whether light is able to pass through them.